Black holes are among the most mysterious and fascinating objects in the universe. They are regions in space where the gravitational pull is so intense that nothing, not even light, can escape from them. This incredible gravitational force arises when a massive amount of matter is compressed into a very small area. The concept of a black hole challenges our understanding of physics and the fabric of space-time, leading scientists to explore and theorize about their nature and behavior. The idea of a black hole begins with the concept of escape velocity, which is the speed required for an object to break free from the gravitational pull of a celestial body. For Earth, this speed is about 11.2 kilometers per second. However, a black hole's escape velocity exceeds the speed of light, which is approximately 299,792 kilometers per second. Since nothing can travel faster than light, once something crosses into the black hole's domain, it can never escape. The boundary that defines the region from which no escape is possible is known as the event horizon. Beyond this point, the gravitational pull becomes so overwhelming that all paths lead inevitably to the core of the black hole. The event horizon is not a physical surface but rather a theoretical boundary that marks the limits of the observable universe around the black hole. Anything that crosses this boundary becomes part of the black hole, adding to its mass and gravitational influence. Black holes come in different types and sizes, each formed under varying conditions. The primary types of black holes are: stellar mass black holes are the most common type, typically formed when massive stars exhaust the nuclear fuel and collapse under their own gravity. These stars, which have masses between about 8 and 20 times that of the Sun, undergo supernova explosions, leaving behind a dense core that may become a neutron star or a black hole. If the core's mass exceeds a critical threshold, around 2.5 times the mass of the Sun, it will collapse further, forming a black hole. Stellar mass black holes generally range from about 3 to 10 solar masses. Supermassive black holes are found at the centers of most galaxies, including our own Milky Way. These black holes have masses ranging from hundreds of thousands to billions of times that of the Sun. The origins of supermassive black holes are still not fully understood, but they are thought to form from the merging of smaller black holes and the accretion of vast amounts of matter over time. Their immense gravitational influence plays a crucial role in the formation and evolution of galaxies. Intermediate mass black holes bridge the gap between stellar mass and supermassive black holes, with masses ranging from hundreds to thousands of times that of the Sun. These black holes are more elusive and harder to detect, but they may form through the collision and merger of stars in dense star clusters or by the direct collapse of massive gas clouds. Their existence is still a subject of ongoing research, with only a few candidates identified to date. Primordial black holes are a theoretical type of black hole that could have formed in the early universe, shortly after the Big Bang. Unlike other black holes, which form from the collapse of stars, primordial black holes would have formed from the collapse of high-density regions in the early universe. These black holes could have a wide range of masses, from tiny, subatomic-sized black holes to much larger ones. Primordial black holes are a topic of significant interest because they could account for some of the dark matter in the universe. The event horizon is one of the most critical aspects of a black hole, defining its boundary and the region from which no information or matter can escape. The term event horizon signifies that any event occurring beyond this boundary is hidden from the outside universe. The radius of the event horizon is known as the Schwarzschild radius, named after the German physicist Karl Schwarzschild, who first arrived the solution to Einstein's field equations that describe a non-rotating black hole. The size of the Schwarzschild radius is directly proportional to the mass of the black hole. For instance, a black hole with a mass equal to that of the Sun would have a Schwarzschild radius of approximately 3 kilometers. For supermassive black holes, the event horizon can span millions of kilometers. Despite this vast size, the event horizon itself does not emit any radiation or light, making black holes challenging to observe directly. At the center of a black hole lies the singularity, a point where matter is crushed to infinite density, and the laws of physics as we know them cease to function. The singularity is where the mass of the black hole is concentrated, and it is characterized by infinite curvature of space-time. General relativity, which describes gravity as the curvature of space-time, predicts the existence of singularities, but the true nature of this point remains one of the greatest mysteries in modern physics. In a black hole, the singularity is hidden within the event horizon, meaning that it is isolated from the rest of the universe. Any object falling into a black hole is destined to be stretched and compressed by the extreme gravitational forces, a process known as spaghettification, until it reaches the singularity. However, the singularity is not a point that can be observed or measured, as the information about the object is lost beyond the event horizon. Black holes are not just objects in space, they are regions where the fabric of space-time is warped to an extreme degree. According to Einstein's theory of general relativity, massive objects cause space-time to curve, and the more massive an object, the greater the curvature. In the case of a black hole, the curvature becomes so steep that it creates a well in space-time from which nothing can escape. This warping of space-time leads to several fascinating phenomena, such as gravitational lensing, where light from distant stars is bent around the black hole, creating multiple images or even a halo of light known as an Einstein ring. Black holes also cause time dilation, where time appears to slow down near the event horizon relative to an outside observer. This effect, predicted by general relativity, has been observed in extreme astrophysical environments, providing further evidence of the presence of black holes. The study of black holes has profound implications for our understanding of the universe, challenging the limits of our knowledge of physics and the nature of reality itself. As we continue to explore these enigmatic objects, we may uncover new insights into the fundamental workings of the cosmos, leading to a deeper understanding of the forces that shape our universe. The formation of black holes begins with the life cycle of massive stars, which are the key players in this cosmic phenomenon. Stars, like our Sun, generate energy through nuclear fusion, a process that fuses hydrogen atoms into helium, releasing vast amounts of energy in the form of light and heat. This energy production creates an outward pressure that counterbalances the inward pull of gravity, keeping the star stable. However, when a star with a mass more than about 8 times that of the Sun exhausts its nuclear fuel, it can no longer support itself against gravity. Without the outward pressure generated by nuclear fusion, the star's core begins to collapse under its own immense gravity. This collapse triggers a violent supernova explosion, one of the most powerful events in the universe. For stars with cores exceeding about 2.5 times the mass of the Sun, the collapse continues unabated, compressing the core into an incredibly dense point, what will become a black hole. The outer layers of the star are blown away in the supernova, while the core shrinks into an infinitesimal point known as a singularity. This singularity is surrounded by the event horizon, the boundary beyond which nothing can escape. While stellar mass black holes form from the collapse of individual stars, supermassive black holes, found at the centers of galaxies, have a different and more mysterious origin. These colossal black holes have masses ranging from millions to billions of times that of the Sun, but how they form and grow remains an active area of research. One prevailing theory is that supermassive black holes grow from the merger of smaller black holes and the accretion of vast amounts of matter over billions of years. In the early universe, dense regions of gas and dust could have collapsed directly into black holes, bypassing the stellar formation stage. These seed black holes would then have merged with others, gradually increasing in mass as they consumed stars, gas, and even other black holes. Another possibility is that supermassive black holes formed through the collapse of massive gas clouds in the early universe, creating black holes with masses much larger than typical stellar mass black holes from the outset. These black holes would then have continued to grow by accreting surrounding material and merging with other black holes during galaxy formation. Regardless of their initial formation, supermassive black holes have played a crucial role in the evolution of galaxies. Their immense gravitational influence can shape the structure of galaxies, regulate star formation, and even drive powerful jets of radiation that extend for thousands of light-years. Intermediate mass black holes, with masses between 100 and 100,000 times that of the Sun, represent a middle ground between stellar mass and supermassive black holes. While their existence has been hypothesized for decades, finding concrete evidence of these black holes has proven challenging. One theory suggests that intermediate mass black holes could form in dense star clusters, where the frequent collisions and mergers of stars could lead to the formation of a black hole with a mass greater than that of a typical stellar mass black hole but less than that of a supermassive black hole. Another possibility is that these black holes could be the remnants of primordial black holes formed in the early universe. Observational evidence for intermediate mass black holes is scarce, but there have been a few promising candidates. For example, the detection of an ultra-luminous X-ray source in a distant galaxy has been interpreted as evidence of an intermediate mass black hole. These objects emit more X-rays than a typical stellar mass black hole but less than a supermassive black hole, suggesting an intermediate mass. As technology improves, astronomers hope to uncover more evidence of these elusive black holes and understand their role in the cosmic landscape. Once formed, black holes can grow and evolve through two primary mechanisms: accretion of matter and merges with other black holes. Accretion is the process by which a black hole pulls in surrounding gas, dust, and other material, adding to its mass. As matter spirals toward the black hole, it forms an accretion disk, a swirling mass of gas and dust heated to millions of degrees by the immense gravitational forces. This disk emits radiation, often in the form of X-rays, which can be detected by telescopes and used to identify black holes. The process of accretion is a critical driver of a black hole's growth, particularly for supermassive black holes. As material falls into the black hole, it loses energy and angular momentum, allowing it to cross the event horizon and become part of the black hole. This process can continue for billions of years, with the black hole steadily gaining mass. Another key mechanism for black hole growth is the merger of two or more black holes. When galaxies collide, their central black holes can eventually merge, forming a more massive black hole. These mergers are accompanied by the emission of gravitational waves, ripples in the fabric of space-time predicted by Einstein's theory of general relativity. In recent years, the detection of these gravitational waves by observatories like LIGO and Virgo has provided direct evidence of black hole mergers, opening a new window into the study of these cosmic events. As black holes merge, they can produce some of the most energetic events in the universe, releasing more energy in a fraction of a second than all the stars in the observable universe combined. The resulting black hole is more massive than either of its progenitors, and the merger can also impart a kick to the black hole, causing it to move through space at high speeds. While black holes are often thought of as eternal, they are not completely indestructible. In the 1970s, physicist Stephen Hawking proposed that black holes could slowly lose mass and energy through a process now known as Hawking radiation. Hawking radiation arises from the quantum effects near the event horizon of a black hole. According to quantum theory, empty space is not truly empty but is instead filled with virtual particle-antiparticle pairs that constantly pop in and out of existence. Near the event horizon, one of these particles can fall into the black hole while the other escapes into space. To an outside observer, it appears as though the black hole is emitting radiation. This radiation causes the black hole to lose a tiny amount of mass over time. For large black holes, this process is incredibly slow, and the amount of Hawking radiation is negligible compared to the black hole's overall mass. However, for smaller black holes, especially primordial black holes, Hawking radiation could eventually cause the black hole to evaporate entirely. As a black hole loses mass through Hawking radiation, its event horizon shrinks, and the radiation becomes more intense. Over time, the black hole would lose more and more mass until it eventually evaporates completely, leaving behind nothing but radiation. This process could take longer than the current age of the universe for most black holes, making it difficult to observe directly. The concept of black hole evaporation challenges our understanding of the conservation of information in physics. If a black hole evaporates completely, what happens to the information about the matter that fell into it? This question, known as the black hole information paradox, remains one of the most profound puzzles in theoretical physics, with implications for our understanding of quantum mechanics and the nature of reality itself. Black holes are not isolated objects, they are deeply intertwined with the evolution of the universe. From their formation in the hearts of dying stars to their role in shaping galaxies, black holes have had a profound impact on the cosmos. The formation and growth of supermassive black holes, in particular, are closely linked to the evolution of galaxies. These black holes can regulate star formation by heating and expelling gas from galaxies, a process known as feedback. This feedback can prevent galaxies from forming too many stars too quickly, shaping their evolution over billions of years. Black holes also play a role in the formation of large-scale cosmic structures. The intense gravitational pull of black holes can influence the distribution of matter in the universe, contributing to the formation of galaxy clusters and other large-scale structures. As we continue to study black holes, we gain new insights into the processes that have shaped our universe, from the smallest scales of quantum mechanics to the largest structures in the cosmos. The study of black holes not only reveals the nature of these enigmatic objects but also sheds light on the fundamental forces that govern the universe. The event horizon of a black hole is one of the most enigmatic and intriguing boundaries in the universe. It represents the point of no return, where the gravitational pull becomes so strong that nothing, not even light, can escape. This invisible boundary marks the edge of the black hole, defining the region from which no information or matter can reach the outside universe. From an external observer's perspective, the event horizon is a critical threshold. As an object approaches the event horizon, it appears to slow down, becoming increasingly red-shifted and dim as it nears the boundary. This phenomenon, known as gravitational time dilation, occurs because the intense gravitational field of the black hole warps spacetime, stretching time near the event horizon compared to a distant observer. To someone far away, it seems as though the object takes an infinite amount of time to actually cross the event horizon, gradually fading from view. However, for the object itself, the experience is quite different. From its own perspective, it crosses the event horizon in finite time, with no dramatic change as it does so. This discrepancy between the perspectives of an external observer and the falling object highlights the peculiar nature of black holes and the complex interplay between gravity and spacetime. The event horizon is not a physical surface, but rather a mathematical boundary. It is defined by the Schwarzschild radius for non-rotating black holes, or by the more complex Kerr solution for rotating black holes, which introduces the concept of an ergosphere, a region outside the event horizon where space is dragged along with the rotating black hole. The event horizon also plays a crucial role in defining the observable properties of a black hole, such as its mass, charge, and angular momentum. At the very heart of a black hole lies the singularity, a point where matter is crushed to infinite density, and the curvature of space-time becomes infinite. The singularity is the point where the known laws of physics break down, and our current understanding of the universe ceases to apply. It is a region where gravitational forces are so intense that they overcome all other forces, compressing matter to an infinitely small point. The concept of a singularity arises from Einstein's theory of general relativity, which describes how mass and energy warp spacetime. When a massive star collapses to form a black hole, the gravitational field becomes so strong that it creates a region of spacetime with infinite curvature. This is the singularity, where the equations of general relativity predict a breakdown in the fabric of spacetime itself. However, the singularity is hidden within the event horizon, making it impossible to observe directly. This leads to one of the most significant challenges in modern physics, the need to reconcile general relativity, which governs the behavior of large-scale structures like black holes, with quantum mechanics, which describes the behavior of particles on the smallest scales. The singularity represents a point where these two fundamental theories of physics come into conflict, suggesting that a more complete theory of quantum gravity is needed to fully understand what happens inside a black hole. The nature of the singularity also raises profound questions about the ultimate fate of matter and information that falls into a black hole. According to general relativity, all matter that crosses the event horizon is crushed to infinite density at the singularity. However, this leads to the black hole information paradox, which questions whether information about the matter that falls into a black hole is truly lost, or if it can somehow be recovered. The black hole information paradox is one of the most perplexing problems in theoretical physics. It arises from the apparent contradiction between general relativity and quantum mechanics regarding the fate of information in a black hole. According to quantum mechanics, information about the state of a physical system should never be lost. This principle, known as unitarity, is a cornerstone of quantum theory. However, general relativity suggests that any information about matter that falls into a black hole is lost forever once it crosses the event horizon and is crushed to infinite density at the singularity. The paradox becomes even more pronounced when considering Hawking radiation, a theoretical process by which black holes can slowly evaporate over time. As a black hole emits Hawking radiation, it loses mass and energy, eventually leading to its complete evaporation. If the black hole disappears entirely, what happens to the information about the matter that was swallowed by the black hole? If this information is truly lost, it would violate the principles of quantum mechanics, leading to a fundamental inconsistency in our understanding of the universe. One proposed resolution to the information paradox is the idea that information is somehow encoded in the Hawking radiation itself, although the exact mechanism for this remains unclear. Another possibility is that the information is preserved on the event horizon, in a concept known as the holographic principle. According to this idea, the event horizon of a black hole can be thought of as a two-dimensional surface that encodes the information about everything that has fallen into the black hole in a way that is analogous to a hologram. While various theories have been proposed to resolve the information paradox, it remains an open question in physics. The paradox highlights the need for a theory of quantum gravity that can seamlessly integrate the principles of general relativity and quantum mechanics, providing a deeper understanding of the true nature of black holes. The singularity and event horizon also bring up intriguing possibilities for the nature of spacetime itself, particularly in the context of wormholes. Wormholes, also known as Einstein-Rosen bridges, are hypothetical tunnels through spacetime that could theoretically connect distant regions of the universe or even different universes altogether. These structures are predicted by the equations of general relativity, although their existence remains purely theoretical. A wormhole could, in theory, allow for faster-than-light travel or provide a shortcut between distant points in spacetime. Some theories suggest that a black hole could be connected to a white hole, a hypothetical object that expels matter and energy rather than absorbing it, via a wormhole. This connection would allow matter to fall into a black hole, travel through the wormhole, and emerge from the white hole in another region of spacetime. However, the stability of wormholes is a significant concern. Most solutions to the equations of general relativity suggest that wormholes would be highly unstable and collapse almost instantaneously, making them impractical for travel. Additionally, the intense gravitational forces near the event horizon would likely destroy any object attempting to pass through a wormhole, a process known as spaghettification, where an object is stretched and compressed by the extreme tidal forces of the black hole. Despite these challenges, the study of wormholes remains an active area of research in theoretical physics. If wormholes do exist, they could provide a means of escape from a black hole or a way to explore distant regions of the universe. The connection between black holes, wormholes, and the structure of spacetime continues to captivate scientists, pushing the boundaries of our understanding of the cosmos. The event horizon poses a fundamental observational challenge. Can we ever see inside a black hole? The very definition of the event horizon suggests that it is impossible to observe anything beyond it. However, recent advancements in technology and our understanding of black holes have opened new avenues for exploring these mysterious objects. The Event Horizon Telescope (EHT) project, for example, has provided the first direct image of a black hole's event horizon. By combining data from radio telescopes around the world, the EHT has captured the shadow of the black hole at the center of the galaxy M87. This shadow represents the silhouette of the event horizon against the bright background of the accretion disk, offering a glimpse into the region just outside the black hole. While we cannot see beyond the event horizon, observing the behavior of matter and light near this boundary can provide valuable insights into the nature of black holes. The study of accretion disks, gravitational lensing, and the motion of stars around black holes all contribute to our understanding of these enigmatic objects. Additionally, the detection of gravitational waves from black hole mergers offers a new way to probe the properties of black holes and the nature of spacetime itself. The horizon problem also raises philosophical questions about the nature of reality and observation. If we can never observe what lies beyond the event horizon, can we ever truly understand what happens inside a black hole? The study of black holes challenges our perceptions of space, time, and the limits of human knowledge, pushing us to explore the boundaries of science and imagination. In summary, the event horizon and singularity of a black hole represent some of the most profound mysteries in the universe. These concepts challenge our understanding of physics, leading to paradoxes and questions that remain unresolved. As we continue to explore the nature of black holes, we may uncover new insights into the fundamental workings of the cosmos, bringing us closer to solving the mysteries of these extraordinary objects. If you enjoyed this video, make sure to check out part 2 for even more insights and exciting content. The Future of Black Hole Research: How We're Pushing the Boundaries of Science Video 2.